And understand how data is stored across Hadoop's distributed clusters. Big data is generated from different data sources. A large file, usually greater than 100 megabytes, gets routed from a name node to data nodes. Name nodes hold the metadata information about the files stored on data nodes. It stores the address and information of a block of file and the data node associated with it. Data nodes hold the actual data blocks. The file is split into multiple smaller files, usually of 64 megabytes or 128 megabyte size. It's then copied to multiple physical servers. The smaller files are also called file blocks. One file block gets replicated to different servers. The default replication factor is 3, which means a single file block gets copied at least 3 times on different servers or data nodes. There is also a secondary name node, which keeps a backup of all the metadata information stored on the main or primary node. This node can be used if and when the main name node fails. Now that you have understood a little about HDFS, let's look at the second core component of Hadoop, MapReduce, the primary framework of the HDFS architecture. A file is split into 3 blocks as split 0, split 1, and split 2. When a request comes in to retrieve the information, the mapper task is executed on each data node that contains the file blocks. The mapper generates an output, essentially in the form of key-value pairs that are sorted, copied, and merged. Once the mapper task is complete, the reducer works on the data and stores the output on HDFS. This completes the MapReduce process. Let's discuss the MapReduce functions, mapper and reducer, in detail. The mapper. Hadoop ensures that mappers run locally on the nodes, which hold a particular portion of the data to avoid the network traffic. Multiple mappers run in parallel, and each mapper processes a portion of the input data. The input and output of the mapper are in the form of key-value pairs. Note that it can either provide 0 or more key-value pairs as output. The reducer. After the map phase, all intermediate values for an intermediate key are combined into a list, which is given to a reducer. All values associated with a particular intermediate key are directed to the same reducer. This step is known as shuffle and sort. There may be a single reducer or multiple reducers. Note that the reducer also provides outputs in the form of 0 or more than 1 final key value pairs. These values are then returned to HDFS. The reducer usually emits a single key value pair for each input key. You have seen how MapReduce is critical for HDFS to function. A good thing is you don't have to learn Java or other Hadoop-centric languages to write a MapReduce program. You can easily run such Hadoop jobs with the code completely written in Python with the help of Hadoop Streaming API. Hadoop Streaming acts like a bridge between your Python code and the Java-based HDFS and lets you seamlessly access Hadoop clusters and execute MapReduce tasks. You have seen how MapReduce is critical for HDFS to function. Thankfully, you don't have to learn Java or other Hadoop-centric languages to write a MapReduce program. You can easily run such Hadoop jobs with a code completely written in Python. Shown here are some user-friendly Python functions that are written for the mapper class. Suppose we have the list of numbers we want to square. We have the square function defined as shown on the screen. We can call the map function with a list and a function which is to be executed on each item in that list. The output of this process is as shown on the screen. Reducer can also be written in Python. Here, we would like to sum the squared numbers of the previous map operation. This can be done using the sum operation as shown on the screen. We can now call the reduce function with the list of data which is to be aggregated, and aggregator function, in our case sum, is used for this purpose. Big data analysis requires a large infrastructure. Cloudera provides enterprise-ready Hadoop big data platform, which supports Python as well. To execute Hadoop jobs, you have to first install Cloudera. It's preferable to install Cloudera's virtual machine on a Unix system, as it functions best on it. To set up the Cloudera Hadoop environment, visit the Cloudera link shown here. Select Quick Start Download for CDH 5.5 and VMware from the drop-down lists. Click the Download Now button. Once the VM image is downloaded, please use 7-zip to extract the files. To download and install it, visit the link shown on screen. Cloudera VMware has some system prerequisites. The 64-bit virtual machine requires a 64-bit host operating system, or OS, and a virtualization product that can support a 64-bit guest OS. To use a VMware VM, you must use a player compatible with Workstation 8.x or higher, such as Player 4.x or higher, or Fusion 4.x or higher. You can use older versions of Workstation to create a new VM using the same virtual disk or VMDK file, but some features in VMware tools will be unavailable. The amount of RAM required will vary depending on the runtime option you choose. To launch the VMware Player, you will either need VMware Player for Windows and Linux or VMware Fusion for Mac. So please visit the VMware link shown on screen to download the relevant VMware Player. Now, launch the VMware Player with the Cloudera VM. The default username and password is Cloudera. Click the terminal icon as shown here. It will launch the Unix terminal for Hadoop HDFS interaction. To verify that the Unix terminal is functioning correctly, type in pwd, which will show you the present working directory. You can also type in ls-lrt to list all the current files, folders, and directories. These are some simple Unix commands which will come in handy later while you are implementing MapReduce tasks.